So we're going to start the equilibrium unit here with just starting out with a simple definition of what equilibrium is. So far throughout chemistry, what we've been learning about is lots of chemical reactions. And all those chemical reactions we've been talking about so far, or at least what we've kind of showed you or told you, is that reactions have reactants and they have products. And that when we mix the reactants together, they make the products. And it's kind of like I start out with just reactants. Then when I mix them together, those reactants undergo a change, a chemical change. And at the end of the reaction, I end up with zero reactants and all products. And so this is what's called a stoichiometric or a quantitative chemical reaction. And stoichiometric, I think, makes really good sense because when we talked about stoichiometry in previous classes, these are reactions where I have these reactants turning into these products and we make calculations based on those. But it turns out that not every chemical reaction is a stoichiometric or a quantitative reaction where all the reactants turn into all products. And so the other type of reaction that we have and what we're going to cover throughout the course of this entire unit are what we call equilibrium reactions. And the definition for this is just simply that an equilibrium is reached when you have a reaction that has a forward reaction or rate, and it's equal to the reverse reaction rate of that reaction. So for this example right here, I have the formation of hydrogen iodide gas. And as I've stated before, what we've learned in the past is that reactions typically are stoichiometric or quantitative. And so we have this one arrow pointing in one direction. But for this reaction, there is also a reverse reaction where eventually over time, as the reactants initially turn into the products, as there becomes more products, the products actually undergo a decomposition reaction and they decompose back into the reactants. And so this is happening simultaneously within a container that this gas, for example, would be contained in. So hydrogen gas reacts with iodine gas to make hydrogen iodide gas. And then simultaneously, while that reaction is going on, other hydrogen iodide gas molecules that would be in that container would be decomposing into iodine gas and hydrogen gas. And so the example that I've got down here below is to just kind of illustrate this so that this concept makes sense. So here along a time scale, I've got the same container at 4 different points in time. So I might be time 1, time 2, time 3, time 4, however you want to denote that. It's totally up to you. It doesn't really matter. It's just a time scale. And so here initially I've got in the container just reactants, no products. So obviously at the start, just the forward reaction is going to occur because the reverse reaction can't occur if there's no hydrogen iodide in the container to begin with. And so this forward reaction will occur, and you can see after a fairly small period of time, you can see that some of the hydrogen molecules, these blue circles, have reacted with some of these iodine molecules, these red circles, to make a hydrogen iodide molecule. So right here and right here. And so you can see after this short period of time, and how much time doesn't really matter, you can see that I've got 4 hydrogen molecules still, 4 iodine molecules still, and now I have 2 HI. You can see at the initial phase, before the reaction began, I had 6 hydrogens, 6 iodines, and 0 hydrogen iodide molecules. And so this has begun to react. Now, because in this container there are now hydrogen iodide molecules there, hydrogen iodide molecules, the reverse reaction is going to start to go. But because there's only a few, the forward reaction is still going to be occurring at a faster rate than the reverse reaction. And so equilibrium has not yet been established. And so if I go to the next place in time, same container, but the reaction has had a little bit more time to progress, you can see that now I've got 4 hydrogen iodide molecules and just 2 hydrogens and 2 iodines. And at this point, what this reaction is showing us now is that it's following our coefficients, where I've got one of these and one of these makes 2 of these. So however many hydrogens and iodines I have, I should have twice as many hydrogen iodide molecules. And that ends up being the case here in this box. Now if I go to the next place in time, same container, same reaction, just further in time, I take a look at this and I can see that I still have 2 hydrogens, 2 iodines, and 4 hydrogen iodides. But you can see that those molecules are not the same ones. So essentially what's happening here is in this box and moving over into this box over time is while these 2 molecules would be coming together to form hydrogen iodide, say this molecule here would be decomposing, and those hydrogen iodide molecules would be separating into hydrogen and iodine. And so at this point, you can see from this place in time to this place in time, overall the number of hydrogens and iodines that I have hasn't changed. Same with the hydrogen iodide molecules. But the reactions are still occurring. I'm still forming hydrogen iodide, but simultaneously while I'm forming hydrogen iodide, I'm also having other hydrogen iodide molecules decomposing into their elements. And so this is a concept of equilibrium, a reaction that's at equilibrium, where the rate of the forward reaction is equal to the rate of the reverse reaction. Now, there's a couple of factors that are needed to achieve equilibrium. These are the 4 on the board. You should write them down. These are important. Number 1 is I have to have a closed system. If I open this container so that more hydrogen or more iodine can come into the reaction, then I'm going to throw the equilibrium off, and the reaction won't be able to achieve equilibrium if I'm constantly taking out or putting things in. So that's one thing. The reversible reaction concept is just simply that. I can't have a reaction that will achieve equilibrium if it will not undergo a reverse reaction. So for example, burning a log of wood, that is a non-reversible reaction. Can't reverse that, and there's no way that you can have like a perpetual piece of wood that just constantly is burning because it's going to burn some and then it's going to form back into more wood so you can burn it again. That's just not the way that works. And so some reactions are not reversible. So a condition to achieve equilibrium is that the reaction you're using must in fact be reversible. And the next thing is once you have those 2 rates, the forward and the reverse reaction, for it to be in equilibrium, these rates must be equal. If one rate is slower than the other, then it's not at equilibrium yet, and you have to allow it some time to have one rate speed up and catch up to the other so that it can be at equilibrium. And then the final point is you just have to have constant properties. If you're changing things like temperature and pressure, then you're going to throw the reaction out of whack, and it won't be at equilibrium at that point too. So that's the concept of an equilibrium reaction, and very base fundamental concept that's needed to understand in order to move on forward throughout this unit. So if you need to rewatch, you can rewatch. Make sure that you understand these concepts of what is an equilibrium reaction and what are the 4 factors that are needed to achieve equilibrium, and you should be fine.